Traditionally, large-scale petrochemical, steel, and geothermal power plants have relied on steam ejectors driven by high-pressure steam present within the plant to create vacuum. However, these systems require huge amounts of motive steam to compress gas from a vacuum state to atmospheric pressure. To reduce motive steam consumption and to improve energy efficiency, hybrid vacuum systems that introduce liquid ring vacuum pumps downstream of the steam ejector have become more common, utilizing the strengths of both the steam ejector and the liquid ring vacuum pump. In this video, a gas extraction hybrid vacuum system comprised of a steam ejector and a Tsurumi liquid ring vacuum pump is used at a geothermal power plant. This hybrid vacuum system consists of 3 first-stage steam ejectors with capacities of 40%, 60%, and 80%. 1 intercondenser with a capacity of 140%, 2 liquid ring vacuum pumps with a capacity of 50% on the second stage, 1 backup ejector with a capacity of 50%, and 1 after condenser. The liquid ring vacuum pump consists of 2 motive units made up of skid-mounted vacuum pumps, gear reducers, and motors. It also has 2 separator tanks. The steam ejector converts the motive steam pressure into velocity energy to generate a vacuum. The pressure energy of the steam ejected from the nozzle is converted into velocity energy, and it flows into the diffuser at a low pressure and high speed. The suction gas in the suction chamber comes into contact with this high-speed steam, receives velocity energy, and undergoing a mixing effect, flows into the diffuser together with the steam. The mixed gas consumes velocity energy in the diffuser, increases its pressure, and flows to the discharge port. Steam and gas ejected from the first stage steam ejector flow into the intercondenser. Water sprayed through a nozzle at the top of the intercondenser cools the mixed gas. The steam in the mixed gas condenses and drops to the bottom of the intercondenser and is discharged from the drain outlet along with the cooling water. The remaining inert gas that is not condensed flows from the discharge nozzle at the top of the intercondenser to the second stage as a saturated water vapor. The discharged gas from the intercondenser is compressed to atmospheric pressure by the second stage vacuum pump. The liquid ring vacuum pump forms a liquid ring with the supplied seal liquid, creating a crescent-shaped space inside. As the impeller rotates and expands the crescent-shaped space, a vacuum is created, and the mixed gas flows into the space through the suction port. After the mixed gas moves towards the discharge port due to the rotating impeller, the crescent-shaped space contracts, compressing the gas to atmospheric pressure and discharging it from the discharge port. Tsurumi liquid ring vacuum pumps are equipped with ball valve mechanisms at the discharge port. In the low vacuum range, the pressure inside the crescent-shaped space becomes higher than the pressure inside the side cover, so the ball is pushed outward and gas is discharged into the side cover. Alternately, in the high vacuum range, the pressure inside the crescent-shaped space is lower than the pressure in the side cover. This pressure is not high enough to open the ball valve, and gas does not flow reversely. This ball valve mechanism prevents overcompression in the low vacuum range and backflow compression in the high vacuum range, high efficiency in the low vacuum range, enabling stable performance, and noise reduction in the high vacuum range. The gas compressed to atmospheric pressure by this mechanism is discharged into the separator tank together with the seal liquid. Gas and liquid are separated in the separator tank. Gas is discharged from the top nozzle of the separator tank, while seal liquid is discharged from the bottom nozzle of the separator. It is through these steps that continuous, efficient operation can be achieved by a hybrid vacuum system consisting of a steam ejector and liquid ring vacuum pump. Furthermore, it is possible to package a small hybrid vacuum system. A shell and tube intercondenser can also be adopted, and a recirculation package with a seal liquid cooler can also be manufactured. Tsurumi makes use of its expertise in vacuum technology to manufacture a quality hybrid vacuum system that is efficient and compact. We will now explain the operation. In this example, the unit is operating at 100% capacity. Initially, both vacuum pump inlet valves are open. First, the inlet valves of the 40% and 60% capacity steam ejector are opened. Next, cooling water is supplied to the intercondenser and vacuum pump. This establishes a liquid seal between the intercondenser and condenser and between the separator tank and condenser. This liquid seal allows gas to flow from the steam ejector to the cooling tower, enabling the vacuum pump to start. Next, the bleed valve in the vacuum pump suction line is opened, starting the vacuum pumps one by one. Once the vacuum pumps start, the bleed valve is adjusted to increase the vacuum. To prevent cavitation damage to the vacuum pump, the bleed valve is adjusted rather than closed completely. After adjusting the bleed valve, the first stage steam ejectors are started. Motive steam is supplied by opening the steam inlet valves of the 40% and 60% capacity steam ejectors. The bleed valve is closed after the turbine starts. This completes the startup of the gas extraction equipment. We are now ready to start generating power. Next, we will explain how to switch from operation with 2 vacuum pumps to operation with 1 vacuum pump and a backup ejector. First, cooling water is supplied to the after condenser, and the backup ejector motive steam inlet valve is opened. Next, the inlet valve of the backup ejector is opened. After starting the backup ejector, the inlet valve of the vacuum pump we will be shutting down is closed. After confirming that the inlet valve is fully closed, the bleed valve of the pump being shut down is promptly and fully opened. After fully opening the bleed valve, the vacuum pump is not immediately stopped, but rather checked for abnormal behavior or a vacuum drop in the condenser. If no abnormalities are found, the vacuum pump can be safely shut down. This concludes the switchover to the backup system. It is possible to switch from the backup system to the vacuum pump again by reversing the process.